Okay. Good morning, good afternoon, all present. Thanks, Caro, for the introduction. Today, we are going to talk about Ray and Python, and we are going to see how to have distributed Python applications deployed on Ray using Kubernetes. So before we move forward, there's a quick introduction for myself. I'm an international tech speaker. As Caro introduced me, I have spoken at various international conferences, including KubeCon, EuroPython, GeoPython, and alike. I'm a distinguished guest lecturer, and also I'm a tech panelist, and I'm very much involved into organizing conferences like EuroPython, GeoPython, and alike. Apart from this, I'm pretty much into research work, and I have around 8 publications to my account. I like mentoring people, and my interest lies apart from computer science in computational neuroscience, high performance computing, and emerging technologies. There's a short disclaimer for this particular talk. The content and the views presented in this talk are my own because it's purely based on the research work that I have done and should not be associated with any of the organizations which I am associated with. The flow of the talk is as follows. We will first see what Ray framework is. Then we will dive into the internals and architecture of Ray framework. We will see how to build a distributed Ray application with a small demo. We will understand what Ray Autoscaler is and how to deploy a Ray app on Kubernetes. All of this has to be done in 25 minutes. So it's this time, but we will try to finish all of it. So let's get started with Ray framework. So what Ray framework is? A Ray framework is pretty much a framework which has been developed by the Rice Lab, which was also responsible. Many of the folks were responsible for creating Apache Spark. And ultimately, it's a general purpose distributed computing and execution framework, and we will understand how it actually works. It's Python first. Some of the components are even written in Java. Some of the components are written in C++, but ultimately, it's a Python first framework for streaming and all. We do utilize Java aspects of it, and it's used to have Python programs. Okay. Yep. Thanks. Okay, so Ray framework is also used as a cluster manager, and today we are going to see how to utilize cluster management utilities like cluster launcher and cluster operator for Kubernetes. It has some great integrations with popular data science platforms, but we are not going to see them. I'll just name them and give you some overview so that you can relate to them. It supports high performance and heterogeneous workloads, and we will see how because it is having support for CPU, GPU, and other workload types as well. And it is actually a very amazing framework because you have low level APIs. Moreover, you have high level libraries, and dynamic execution actually works perfect, which means if you have to execute a program wherein you are following an active framework of distributed systems, you can have classes and then you can have remote execution done for them. And when you have remote execution done, you can have multiple instances of classes run or multiple functions inside the classes run, which we call as tasks. So classes are known as actors and functions are actually known as tasks. And these tasks and classes can or actors can work together, maintain state, and you can have multiple tasks running parallelly on different processes, or it could be even different machines, and the data can be shared across them. So data shareability is another aspect of this framework which many other frameworks lack. So why Ray? Ray is actually a distributed computing oriented framework. So if you want to parallelize your workloads, and then you want to even utilize your existing Python code without doing much modifications, you can utilize Ray. It's highly fault tolerant and it's highly available as well, and we will see some aspects of it. There are some aspects wherein the fault tolerance is not up to the mark, but we will see and we will analyze where we can leverage the fault tolerance and high availability aspects of this framework. You can have multiple machines and multiple data centers, as I have mentioned earlier, and it is like you can actually have one task decomposed into parallel tasks just to speed up computation. So if you were to do a task on Python, essentially Python effectively is a single threaded, you can say, application because of the global interpreter lock, but you can have utilize the Ray framework because of which you can parallelize these tasks. You have other libraries like multiprocessing and Celery also, which do something similar, but data sharing between these processes and the actor framework is something which is not present. And you, if you want to do that kind of thing, you ultimately need to go with a complex architecture, right? So Ray is something which is very seamless. It has many integrations in place, and it's very effective when you talk about distributed computing. And it has many out of the box libraries, even for machine learning tasks, AI tasks. You can have reinforcement learning related libraries integrated, hyperparameter tuning. You can have supervised learning. You can have model serving. You can have data preparation related stuff. So there is something called as Ray data, Ray serve, Ray tune. We will see all of them shortly. Okay, so yeah, here it is what I was talking about. So you have RLlib, which is basically a reinforcement learning library, which Ray is offering. You have Tune, which is hyperparameter tuning. So if you were to use HyperOpt or Optuna, you can actually uh, instead have Ray Tune utilized, right? You have Ray Serve for serving ML models. You have Ray Train for training supervised machine learning and deep learning frameworks and models. You have Ray datasets, which is essentially built on top of Apache Arrow. And you have these data sets created so that you can have data prepared, you can clean them, you can transform, and ultimately feed to your data, your model. And you have Ray workflows, which is more or less like a workflow scheduling system. But if you want some sophisticated scheduling, Ray even has integration with Apache Airflow. So you can utilize the Ray provider for Apache, and Apache Airflow will utilize Ray workers and Ray cluster for running those workflows, right? So this is mostly how the Ray framework related ecosystem looks like. You have third-party library integrations, as I mentioned, and this actually is just a direct mapping for the labels that I showed here, or the categories that I have here. And ultimately, Ray is something which sits between your platform and between these libraries, and you can have tight integrations done, or you can even have cloud agnostic or vendor agnostic integrations done as per your will. So the big picture is, and this is something which we need to understand today, because this talk is more focused on auto scaling aspects of Ray and not the coding or actor framework aspects of Ray, nor it has to do anything with the machine learning aspects as such. But we, in general, we will see the architectural aspects of Ray and how we can utilize that on Kubernetes. So this will be more of uh, how the internals of Ray work with respect to architecture, how it is laid out on Kubernetes, and ultimately how we can run tasks on Kubernetes using the Ray autoscaler. Okay, so the big picture is that we have a Ray cluster in which we have one node which is called as head node, and we have multiple nodes. We can have multiple nodes which are worker nodes. Head node has something called as a driver, which is essentially a component which drives, you can say, the scheduling aspects of things. And we will drill down into more into components. And workers are the ones which are actually the processes which will run your uh, Python tasks, right? Then specifically talking about a worker node has something called as a raylet, and raylet is actually present on even the head node. Okay, and you have worker, and worker is actually having two components. So one is ownership table and one is in process store. So in process store is very much the object store that is there for each worker process that runs inside the worker node. And then you have ownership table, which actually resolves the dependencies, takes care of dependencies of the tasks, the Python tasks that are running inside a worker. And you have raylet, which actually is chained. So raylet of every worker node actually interacts with each other. They sync data because it's a distributed component. So multiple worker nodes are chained together, and the raylet components of them are actually interacting with each other. And you have something called as task scheduler, which is for scheduling tasks on worker nodes. It even reports back to the head node that, okay, whether I have resources or not, whether the worker node is able to schedule more number of tasks or not. And likewise, you have something called as object store, which is for storing the worker node specific or worker node related metadata objects. It could be even your object references that you want to store on the worker node, or during the computation, the object references which are getting stored, and you can have them stored in object store, and it could even have metadata, and that metadata could even be different than what is stored on other node. But then if you want the data to be shared, it's like a shared storage. So this object store which we have here, it's a shared storage. So it can have data for this particular worker node, but if at all there needs to be some data sharing that needs to happen between the worker nodes, this could even act as a shared object store. Then you have something called as head node, and coming to the head nodes architecture, this has additional component which is called global control store, and again, it has the cluster related metadata, and it's essentially a Redis implementation. And apart from this, it also maintains the data related to again the resources that are there, and uh, so Raylet is actually the one which will tell, okay, go ahead and schedule some worker process. And when we talk about worker process, those are these yellow boxes. And worker processes can reside on head node, but as a best practice, head node should not be having worker processes, and ultimately the worker processes should be hosted on the worker nodes that can reside uh, in your cluster anywhere. Just the connectivity between these nodes need to happen. So if we talk about a top level view of how these components are structured in terms of layers, the task execution is actually done by workers. Driver is not a task executor as such. Only the workers or the worker processes executes the task. We have something called as a resource manager layer, wherein we talk about task scheduler, which takes care of even how much resources are left, how much resources are being utilized on the worker node, and this is something which task scheduler takes care of. The memory management aspect of the workers and related node is done by the object storage, as we saw. And then there is metadata management layer, which also stores the cluster wide configuration, and it's a Redis implementation which we call as global control store. So coming to Ray autoscaling, in the architecture which I showed, it didn't mention about the autoscaling component because it's something which, depending on how you implement your cluster autoscaler, the process or the autoscaling component is kind of placed. So Ray autoscaling, just like any other autoscaling, or just like it could be considered closest to the Kubernetes way of autoscaling, is just uh, there to support the highly elastic workload nature, wherein you want the cluster to have auto scaling capabilities so that you can terminate nodes, you can start new nodes, you can launch or restart nodes depending on the utilization of the cluster which is happening. And if there is more demand, then you can go ahead and you can have more number of nodes. And if there is less demand, you can have the nodes downscaled. This ensures actually that the workloads have sufficient resources to run. So if, say, you have a task which requires GPU, or if you have task which requires two CPU, but you don't have a worker node which has two CPUs available, you will have a worker node created because of the auto scaling nature. If at all it lies in the count, the min max count that you have specified. So you can say that you have min count of 2 worker nodes and you have max count of 50 worker nodes. And ultimately, if there is room, if you have not reached those 50, the limit of 50, you can have the autoscaler scale your worker nodes to the extent it actually requires. This also is effective for minimizing the idle resources. So basically, downscale can happen when you don't have anything working inside the cluster, and it performs load-based auto-scaling. So mostly, ultimately, in the background, it's a bin packing algorithm which is working, and you see that if a node has capacity in terms of the resources, it will go ahead and it will schedule, and even it can schedule multiple processes or multiple tasks on a single node. Uh, just the thing is that the resource should have adequate resources. The node should have adequate resources, and it should have it should meet the criteria. So if it's a GPU intensive task and we have the task to be run on GPU, it should run on a worker node which has GPU. It should not be that it should get scheduled on a worker node which doesn't have a GPU, right? So all of these things are taken care by the autoscaler component, and ultimately because of this you have quite effective cost, you can say, incurring. So because if you don't have worker nodes which are required, your worker nodes are scaled down, and then you minimize the cost, and basically your aim is to maximize utilization and minimize the cost or optimize the cost. So this is how a Ray cluster looks like. You have something called as cluster configuration YAML, which is just a YAML file specifying which cloud provider you want to interact with, what is the region, what's the project ID, what are the resource specifications, like how many number of worker nodes, min max, what should be the type, whether it should be M4X large or M4 2X large. If you are talking in terms of AWS, or if you are talking in terms of GCP, it should be say N2 standard or E4 standard. Likewise, so you just specify these things. You can even control uh, the speed at which the scaling or downscaling happens. So you can say that you can control the speed using some flags that are there in the cluster configuration. And there is this good blog which talks about differences between cluster autoscaler and Kubernetes autoscaler, specifically from a Ray perspective, and how they differ. And this has been adapted from there. So you have something called as Launchpad. Launchpad could be any server which you are using to run the Ray server, and ultimately you have Ray CLI which you can utilize. You start Ray CLI by saying Ray start or Ray up, and the cluster comes up. That cluster should be coming up in the cloud that you have provided. So if you have provided in the cluster YAML, it's a GCP cloud, it will go ahead and it will have the cluster resources created in a GCP project. What this creates is that it creates a virtual machine instance, which will be called as a head node, and then the head node actually has autoscaler component running as a background process. So this is something which I didn't show in the previous architecture, because depending on whether we go with cluster launcher, which is basically this procedure, or there is another procedure of launching the Ray cluster using Kubernetes operator. So depending on how you are bringing up your Ray cluster, the placement of autoscaler actually changes. So in this case, you have one head node, and in general, in Ray, you have only one head node, and this becomes a single point of failure. If the head node goes down, you don't have the coordination, because the autoscaler will also go down and the worker nodes would become orphan. So head node is very critical, and as of now in Ray, only one head node is there, and it's the single point of failure. Uh, Coming to worker nodes are essentially hosted as EC2 instances, and these are controlled by autoscaler. So if you have worker node count set as 2, and you have max count set as 50, depending on the utilization and demand, it will go ahead and it will upscale downscale the worker nodes. Now this is the architecture which is of interest to us, and which will serve as a base point for us to go ahead and start the demo. So we will next look at demo, and this is the architecture which we will be taking care, having a look at. So let's say you have cluster configuration YAML specified for two Ray clusters, one is A and one is B, and this actually is something which you are defining, and ultimately Ray clusters are CRD implementations. So you have two things when it comes to Kubernetes operator. One is Ray K8's operator, one is called as a Ray cluster. Both of them are CRDs, and these are the two main pillars of Kubernetes implementation of Ray. You have the cluster configuration passed or made part of the Ray cluster CRD, and ultimately you have the K8's operator. And the difference you see from the previous architecture is that instead of the autoscaler being placed on the head node, it is now something which is placed on the Kubernetes operator. And Kubernetes operator is essentially implemented as a pod workload only. So now because of this, at least you have one additional advantage when compared to the cluster launcher, that uh, if at all head node is going down, then in that case the ray operator would be bringing back the head node, but the autoscaler component would still be working, right? So because of this, the failure, or the effect of failure that we had in the cluster launcher mode, or the pattern of launching ray cluster, is reduced, and ultimately it's better in terms of reliability if you have a ray operator, Kubernetes operator, and you are hosting this in Kubernetes. And essentially, instead of having these head node, worker node hosted uh, one-on-one fashion on virtual machines, you have these hosted as Kubernetes pods, right? So here again, there is a difference. So you could have Kubernetes worker node, which could be hosting multiple ray pods, and ultimately these pods are nothing but the worker nodes or the head nodes, right? And then a single ray operator can actually have multiple ray clusters managed, which is a good thing. And then where you deploy this operator is up to you. By default, it's a cluster scope thing, but you can even have a namespace scoped ray operator. And this gives you freedom of running multiple ray operators in different namespaces. And this again is something which is followed in production. So one should not be having array operator cluster wide deployed. Instead, one should have namespace wide deployed, and then from that you can have multiple clusters, array clusters deployed in the namespace. Uh, so let's go ahead with the demo portion. So what I have with me is a cluster, a Kubernetes cluster, and let me zoom in. So I have a cluster which has a couple of nodes, okay, and I have deployed this cluster in GCP. So you see that I have multiple Kubernetes uh, nodes with me. What we have to do is we have to go and we will utilize the Helm chart which comes with Ray. So this is available on the official repository. You do Helm Ray install, and ultimately you pass the reference to the directory or Helm chart. This brings up a Helm release. So I have already deployed, so because we had less time. So if we do Helm list, it will give us the releases, and our cluster is called PyCon Ray cluster 00. Now it has also created a namespace because we were supplying namespace, and we chose to create a new a namespace. So if we just see the pods which are running, so you have head pod and you have worker pod. There is something which is job. So let me delete it because I'll be creating a new job, and we will see what ultimately we will be doing is we will be having, and let me go to the code. The code for this is something which is available, uh, and I'll just show you what the code is doing. It's just a pi estimation, so the value of pi can be estimated through this code. It's a very simple implementation. We are using NumPy, but we are least bothered about this function. What we are doing is we are converting this function estimate pi into a ray function or a distributed function by having a decorator mentioned at the top of this function. So ray remote actually converts a function to a task, which means a distributed task in ray. And then if you just define ray remote at top of a class, it actually turns the class into an actor or distributed actor. And then any function under that class will become a ray task, right? So what we are doing is we are saying that ray remote is the decorator which we are applying to our function, and then we are calling ray estimate pi. Now you see that instead of simply passing the number of samples here in, we do something special which is dot remote. And this is a way how you call the tasks in ray, or how you call the classes in ray, so or actors in ray. So you just have to include dot remote, and then in remote you actually pass your parameters to the function. And this dot remote is just a thing that you need to do. You see that we have reutilized our existing code, which was just estimation of pi. We have just added a decorator on top of it, and then we are calling that function in a bit different manner. Instead of utilizing the function directly with the parameters, we are adding another function which is remote, and to that function we are actually passing our parameters. So what it does is it takes sample sizes 10,000 and 100,000, and it applies estimation of pi on top of this. And then what you get from ray estimate remote when it's a task is the futures. So in Python, futures, we term them as object references. So you are getting object references, and ultimately, after you get result for both of them, or any tasks that you are performing, right? These two tasks will be performed parallelly, and we will see shortly. These two tasks are being performed parallelly, and if you just increase the number of elements in this list, or maybe you make it more complex, or you make it more compute intensive, those tasks will be run parallelly in different worker nodes or worker processes. And ultimately, once we have output from all these tasks, the computation will be returned as an object reference in futures, and then we just receive those futures and value of future from dot get. So dot get is another array function that returns the value of the futures of the object, or the object reference that is there, and ultimately we get the value, and that's all. So what we will be doing is we will create a Kubernetes job, right? And this is the job. It's very simple. What you do is you just name the job, you take the Ray project image, and you pass the arguments. An argument, it's just doing a wget on this GitHub repositories file estimate pi that we just saw, and it is just running. And then since that file actually has a Ray library imported, and moreover, how we are calling the main function is we are first initializing ray, and then we are calling main function, and it has a remote decorator as well. And how we are calling this function is through the remote function. This will actually work as a ray a distributed task, and you will see the distribution happening. So what I have done is I have my Kubernetes cluster here. I will actually start port forwarding, and let me take the command quickly. I have it for reference. So this command is actually going to forward the head service which is there. So let's do kubectl get service, and you will see that for the head pod we have a service. So once we have the service, once we have the service running, we will actually see a dashboard like this. And this dashboard actually gets refreshed each time, and it shows the number of workers running and what's the core utilization, what's the head node, what's the worker node. And in our case, okay, we have the dashboard running. So okay, and we have, I'll just make a watch on Kubernetes pods, and I'll just deploy this, which is the last section. So we are just going to create a Kubernetes job, and we are going to see the output of the job. You see that a job is getting started, it is running, and ultimately it should be running the Ray processors as well. So let me go, and there seems to be some port forwarding issue, but you see that the task actually executed, and we have the values of pi calculated, right? So this is a short demo. I think I'm just about to get over in terms of time. But let me try. This dashboard should be loading, and basically this job actually did the computation, which should have taken some more amount of time, but it did it very quickly because it had uh, roughly 3 workers, right? Because head itself is acting like a worker here, and because of this, it was able to execute this task very quickly. Once the dashboard is up, I should be able to uh, show you. Let me. Okay. There seems to be some issue. So yeah, that's pretty much it. Any questions you have? I'm up for questions.